Good day, everyone. You're welcome to my YouTube channel. Today, we are considering dimension of physical quantities. In another word, we can call it dimensional analysis. And to start with, we have two types of physical quantities in physics. We have fundamental quantities, which is also known as basic quantities, that is the quantities that give rise to other quantities. We also have a derived quantities, which is the combination of two or more fundamental quantities. And the unit of fundamental quantity is known as fundamental units, while that of derived quantity is known as derived units. The table that you can see on the screen, we have fundamental quantities, examples of some fundamental quantities, their symbol, unit, and dimension. Now, what is very, very important to us on this table is the unit and dimension. What this table is telling us is that, let me quickly take us through that. Mass, the unit of mass is a kilogram. The unit of mass is kilogram. And as a result of that, anything that is measured in kilogram, anything that has its unit as kilogram, has a dimension of capital letter M. That's the meaning of that. Because when we get to dimensional analysis, whatever that is measured in kilogram will have a dimension of capital letter M. So also length is measured in meter. Length is measured in meter. And length could be any distance, that is vertical distance, which is referred to height, the radius of a circular shape, circumference, length, breadth. Anything that is measured in meter is under this category here. And whatever that has its units as meter has a dimension of capital letter L. Take note of that. Now the third one is time, which is measured in seconds. Time is measured in seconds. And the dimension of anything that is measured in seconds is capital letter T. Let's take note of that. And so also others are also there. Okay, let's move away from this. Let's quickly look at the table that is having derived quantities, their symbol, formulas, and units. As you can see on the screen, we have a table for derived quantities. And when we say derived quantity is a combination of two or more fundamental quantities. As we can see, area, this is the formula for area, that is combination of two lengths, that is length multiplied by breadth. So that makes the unit to be m squared. And remember, we've mentioned it previously that whatever that is measured in meter has its dimension to be capital letter L. Now in this case, now we have a meter square, so the dimension will be capital letter L square. In the case of volume, we have combination of three lengths, which is length, breadth, and height. And the unit will be meter cube. The dimension will be capital letter L raised to power 3. Now, in the case of speed, speed is defined as a distance over time. And this is the formula. Now, distance is represented with small letter s as a symbol. So, speed is equal to distance over time. And in that regards, we have the unit of speed to be meter per seconds. So that's why we have the dimension as capital letter L per capital letter T. That is, you can as well write it as L over capital T like this, but it's still the same thing as what is on the table. And similarly for acceleration, the formula for acceleration is velocity over time. Let me quickly shift this one in. Velocity and speed, they have the same dimension. Velocity and speed, they have the same unit and the same dimension. So okay, now the acceleration, which is velocity over time, we can, for the under this topic, we can say speed over time. And for that, it means the unit of acceleration will be meter per second square. And remember that anything that is measured in meter has a dimension of capital letter L, and anything that is measured in seconds has the dimension of capital letter T. Okay, so that is why we have the dimension of acceleration to be LT raised to power minus 2. That is, you can as well write it as L per T square. So, moving away from that, we have a force, which is equal to mass multiplied by acceleration. This is our acceleration, and anything, now our mass is measured in kilogram. Acceleration is measured in meter per second. So anything measured in kilogram, the dimension is capital letter M, while acceleration is LT raised to power minus 2. That is why our force is MLT raised to power minus 2. And lastly, on this table, we have density, which is mass over volume, and the unit to be kilogram per meter cube, and the unit to be meter. The dimension will be capital letter M per capital letter L cube. So take note of that. Anything that is measured in kilogram has a dimension of capital letter L. Anything that is measured in meter has a dimension of capital letter L. Anything that is measured in kilogram, dimension of capital letter M, and anything that is measured in seconds has a dimension of capital letter T. Let's take note of that. Okay, moving away from this, let's just consider some examples that are very, very important. Let's see the likely questions that you can come across in your WAEC, NECO, and some other examination. Now, in example number 1, we have to state the dimension of the following physical quantities. The first one is pressure, and the formula for pressure is force over area. Pressure is equal to force over area. The second one is kinetic energy. Kinetic energy is given as half mv square. Power equal to energy over time. Okay, let's take them one after the other. Pressure, which is force over area. If you look at the previous table for derived quantity, their units and their dimensions, you see that on that table, the unit of force is kilogram meter per second square, while that of area is meter square. So the dimension of force is MLT raised to power minus 2, while that of area is L square. So putting them together, it's like having MLT minus 2. Okay, let me do it in in a way that will be very, very clear. It means you're having ML raised to power ML over T square multiplied by okay, sorry, we have our ml over t square divided by l square, and mathematically we know that this will just be equal to something like this, 1 over l square. So taking 1l from here, we are going to be left with 1l. That is why we later have m over t square L. So that is what this one simply represents. So we just use the law of indices to transform it from here to here. That is what just happened. Now for kinetic energy, which is mv square, whenever you have a number in a formula of any physical quantity, number is dimensionless because they are constants. Number is dimensionless. Take note of that. So in the case of kinetic energy, this half will have no dimension. So in the formula of kinetic energy, this small letter m represents the mass, which is measured in kilogram, while v represents the speed, which is measured in meter per seconds. Now the dimension of mass or anything measured in kilogram is capital letter M, while the dimension of speed is LT raised to power minus 1. Bringing them together, we have ml square t raised to the power minus 2, because in the formula we have a v squared in the formula. So that is why we have to square this side, and we have this one as our answer. So for power equal to energy over time. Thank God we've derived the dimension of energy here. Anything energy will have this same dimension as kinetic energy. Name it potential energy, any type of energy. So why it is called energy, it will have the dimension of this kinetic energy. So we can use the dimension derived here in place of energy in the formula of power over time. So that's why we have this over t. So mathematically, this over this will give us this. That is for question number 1. Okay, moving away from question number 1, let's consider another example. This one is one of the most recent WAEC question. The question says, velocity phi of a wave in a stretched string depends on the tension T in the spring and the mass per unit length mu of the spring as shown in the equation below. So the equation is phi directly proportional to t raised to the power a mu raised to the power b. So we have to obtain an expression for v in terms of capital letter T and mu using the method of dimension. That is question number 4, WAEC 2020. That is theory question, part A, question number 4. So from this expression here, from the expression given in the question, capital letter T represents tension. And remember, tension is a type of force, and mu, as defined by the question, is mass per unit length, that is mass over length. Tension is a force, take note of that. So every force, any type of force, will have the same dimension, and we've derived the dimension of force in one of the tables that we've treated previously in this video. And mu is mass per unit length, that is mu will be equal to mass over length, and dimension of mass is kilogram. So unit of mass is kilogram, and the dimension will be capital letter M, while length is having dimension of capital letter L. So bringing all this together, we resolve this expression into equation, that is v equal to k into t raised to the power a mu raised to the power b. K is a constant in that equation and it is dimensionless, so we do not really have to worry about k. So the dimension of speed from one of our tables is Lt raised to the power minus 1. That of tension, because tension is a force, the dimension of tension will be mLt raised to the power minus 2, while that of mass per unit length will be m L raised to the power minus 1. That is m over L. That is dimension for mu. So that is what we have here. Okay, now to solve this problem, we have to equate the powers on both sides. What do I mean by equating the power on both sides? That is, whenever you see L here, you equate the power of L on this side, on this left-hand side, to every L that you can see on the right-hand side. Wherever you see T here, you equate the power of the T on the left hand side to all T's that are present in the left hand side. That is the essence of equating the power, and also do the same thing to M. Okay, equating the powers on both sides. For T, the power of T on left hand side is minus 1, while the power of T on right hand side, we have minus 2a, because if you look at it very well, this is T, is carrying minus 2, and outside the bracket we have a. So minus 2 multiplied by a will give us minus 2a. So, and if you check, there's no other T on the left hand side. It means we have minus 1 equal to minus 2a, and that makes the value of a to be equal to half. If you consider L also, on the left hand side, the power of L is 1. On the right hand side, the power of L here, let me remove this, the power of L here will be equal to A, as you can see outside there, and the power of L on this side is equal to minus B, because L is carrying minus 1. Minus 1 times B will be minus B. So that is why we have this equation here, and from this equation we can rearrange it like this, which means, and we've gotten the value of our A in the first expression or first equation. So putting half in this equation here, we're going to have the value of our B to be half. So that is even enough for us to go with, because we are just looking for A and B, but you can still consider M as well. M on the left hand side, there's no M on the left hand side, so the power will be 0. So on the right hand side, we have M here, which is carrying the power of A, M here, which is carrying the power of B. So the bracket here simply represents multiplication. If you use the knowledge of indices, you know when you have multiplication between an expression, their power will be added together. That is why we are having this. Okay, and from here we can see that our A equal to minus B. Since our A equal to half, it means that our B will be minus half. That is what we did there. And from that one, bringing the value of the power, that is the value of A and B, back to the expression given in the question. Remember, this is the expression given in the question. This is the position of A, this is the position of B. So that's why we rearrange the expression in this form. And having this, remember that anything that is raised to power of half, if x is raised to power of half, mathematically that is root x. And if y is raised to power of minus half, mathematically that is equal to 1 over root y. So that is what happened here. T is raised to power of half, T is raised to power of half, and mu is raised to power of minus half, and that is what makes us to have this equation, which means the relationship between the velocity, tension, and mass per unit length is given as V equal to root of T over mu. Okay, moving away from this, let's check another example, which is also one of the most recent WAEC question. Okay, the question here says, the effective potential energy of a lunar satellite of mass m1 moving in an elliptical orbit around the moon of mass m2 is given below. We are to determine the dimension of capital letter K in terms of other quantity. That is WAEC 2022 question number 3. That is the part A of the theory. Okay, now the expression is given here. You can see that on the screen. This E, which is potential energy of a lunar satellite, is equal to these two expression here. That is, this represents the value of our E, and we are to find the dimension of K in this equation. And the wise thing to do is to make this K the subject of the formula, but let's just take it bit by bit. But before we move on to that, this G is gravitational constant, and it has a unit of Newton per meter square per kilogram square. But since we've not been dealing with Newton in this video, we need to break the Newton down. Newton is a unit of force, while meter is a unit of distance or length, and kilogram is a unit of mass. So breaking this unit here down, we have a derived unit for it, and this is the derived unit for it. Okay, now that is why we are going to be using this in the place of capital letter G, which is gravitational constant. Okay, now from this equation given here, we can cross multiply and have something like this, and that is what we did. We cross multiply here to have something like this, and with that we now consider the dimensions of everything that is in this equation. K is what we are looking for. We don't know the dimension of K, so we are looking for that. So the dimension of R is a radius, and that is a distance or length. So it shares the same dimension with length, so that is why it is represented with capital letter L. Okay, like I said in the previous example, when you have a number does not have a dimension. So we are not going to consider these two in our dimensions, because number does not have any dimension. So from there, we have the dimension of, here we have our m square, that is m1 multiplied by m1 here. That will give us m square, and we have our We also have our R. Okay, now bringing in the dimension of capital letter G into this equation, bringing in the dimension of capital letter G into this equation, so we are going to have this is the dimension of our G, and G is occupying this position, so we need to break it down bit by bit. So this dimension here represents the dimension of G. Okay, now you can see from G that it's having one of its unit as m cube, and that the dimension of m is capital letter L. We have per kilogram, which is capital letter m raised to the minus 1, per second square, which is capital letter T raised to power minus 2. Okay, and we also have in this equation here, we have m1 raised to power 2, we have m2. Both m1 and m2, they represent mass of two different objects. So the dimension for mass is capital letter M. So bringing the two of them together, we have m cube, and radius is also having the same dimension as length, so that's why we have L square here. Okay, taking the both sides into consideration, here we multiply everything that the same together. So m cube L raised to minus 1 will give us m square. L raised to power 3 and L raised to power 2 will give us L raised to power 5, and T raised to power minus 2 is there. Okay, now taking L away from both sides, at least we have 1L, taking 1L out of the right hand side, so we are left with this equation here. So moving away from this, we can make our K, we can have expression for our K, and that is what is here. We have expression for our K, and making K the side of the formula, it means we are going to find the square root of the other side, and that is why we are putting raised to power half here. And putting this raised to power half, it means we are to, okay, now with for m that is having carrying square, if you say 2 divided by 2, you are going to have just m. Also L that is carrying 4, and it's raising to power of half, so we have 2 here, 2 here, that's why we have L square. In the case of T raised to power minus 1 that is carrying half, so that's why we are sorry, to the T raised to power minus 2 that is carrying half, this will take this one away, that's why we're having T raised to power minus 1. That is what we just did to everything there, and we have the dimension of our K to be ml squared T raised to power minus 1. This represents the dimension of our K. Okay, let's move to the last example. Let's check the last example in this video. It's also a WAEC question, recent WAEC question. This just concluded WAEC 2003, and the question is from question number 1 there. The question says, the force F acting on the wing of an aircraft moving through air of velocity v and density rho is given by the equation F equal to k v raised to power x, rho raised to power y, and a raised to power z, where k is a dimensionless constant. So k does not have any dimension, so we do not really need to worry about k. And A is the area of the wing of the aircraft. So capital letter A represents the area. Use dimensional analysis to determine the value of x, y, and z. Well, to find the value of x, y, and z, that is WAEC 2023, question number 1. So this is the expression given, this is the equation given in the question. And according to the question, k is dimensionless, so we do not really need to worry about k. So checking for the dimensions of everything, according to the question, F is a force, so dimension of force is mlt raised to power minus 2. Now v, according to the question, is a velocity. According to the question, the dimension of velocity is lt raised to power minus 1. And what else? Okay, the rho in the question is representing density. Dimension of density is ml raised to a minus 3. You can check the previous table. And we have our area. The dimension of area is L square. And each of them is carrying the power of x, y, and z. So We can as well equate the power on both sides from this equation. We can equate the power on both sides. Doing that, for m, on left hand side, m is carrying the power of 1, and on right hand side, m is just carrying the power of y. So that is what makes 1 equal to y, that is y equal to 1. So for t, on left hand side, t is carrying the power of -2, and on right hand side, t is carrying the power of minus x, because this -1 multiplied by x will give us minus x, and that makes the value of x to also be equal to 2. Okay, now for L, on the right hand side, L is carrying the power of 1 here. So, and on the right hand side, L here is carrying the power of x. L here is carrying the power of -3y, while L is carrying the power of 2z here. That is why we have x minus 3y plus 2z. Remember, in indices, whatever that is happening multiplication sign between them, their power will have addition sign. But just because this is -3, so the minus there will cancel the addition sign. That is what we are having there. Okay. Now, since our y equal to 1 and our x equal to 2, we can substitute for x and y in this equation here. So that is what we did to have this equation, and that will make us to have 2 equal to 2z, and makes our value of z to be equal to 1. So the value of x, y, and z will now be equal to 2, 1, and 1 respectively. That is what we did. And with that, we come to the end of the topic. But just before we go, let me quickly introduce to us a very good physics practical book. The name is Refined Physics Practical Book. The book is structured in line with WAEC, NECO, and Cambridge IGCSE syllabi. And this book is very, very good. It covers everything that has to do with practical for school candidate, that is WAEC and NECO candidate, and also for private candidate, that is GC and NECO GC candidate. So the book is already in use in some schools in Lagos and Ogun State. So if you need the book, you can see some contacts on the screen. Please just reach out to us using these contacts on the screen, or if you care for the soft copy of the book, you can easily access that on Amazon using this web address. The book is also available on Amazon. Okay, and also other service that we offer from Revan Physics Tutor. We have a virtual teaching platform, that is online teaching platform. We handle syllables such as WAEC, NECO, UTME, Cambridge IGCSE, A-Level, and some other programs. Just reach out to us through the number that is on the screen if you want to have any of our online classes, and we'll make it very, very simple for you. We are available on any platform. You can make use of Zoom, Google Meet, WhatsApp, or any platform of your choice. Also, all what we've discussed so far in this video about dimensional analysis, everything is compiled together, and in all our previous video and all the subsequent video, we have a compilation of a comprehensive note for all students or even teachers that are interested in it. The name of the note is a Reform Physics Note. You can just contact any of the number that has been displayed on the screen if you are interested in the note, and we'll discuss. Just call any of those numbers. It's a comprehensive note that have every information that is in all our videos that we've been posting on this platform. So the book is very, very good. It's just a brief note for the students that are preparing for any of the exam we've been talking about, and teachers can as well make use of the note. On this note, we will bring the video to an end. Thanks for watching.